what at the top?
0.1.
Yeah, 0.10. Wow. Then you go down to 60. 1.671. There you go. Where'd you go? Jeff? There you are. So that's across from 60. And that's in the 10% column. I like it. So I know T is 1.671. I know X bar is 2.17. I know S is 0.98. I know N is 61. I just know every damn thing. All right. So now I just plug all this stuff in. So you got X bar, give or take, T times S over square root of N. You got, by the way, obviously, hopefully it's obvious. Why am I allowed to do this? Yeah, that's bigger than 30. Check. Oh, I got it. So then we got 2.17, give or take, 1.671 times S 0.98 divided by the square root of N, 61. How's that going? Is that all right? So how far off? What's our error? Somebody do that already? What'd you get again? 0.2. Yeah, 1 is fine. It's got to be 2.1. And now you just add and subtract that. I mean, this is nice. I mean, let this be nice. The freakiest part, the place where people mess up the most is just plugging the numbers in the wrong place and then using Z or T when they're supposed to use the other one. Now, there are very creative people that have other things that get wrong, but that's the most common things. 2.7 minus 0.21 is 1.96, and then 2.17 plus 0.21, 2.38. So you can always write that little interval. You guys remember interval notation? That's really all that is. Interval with the brackets and the parentheses. You guys remember that? So that's interval notation. That's why it's a confidence interval. Now I can write the statement. We are 90% confident that the interval, 1.96 pounds to 2.38 pounds, contains a true mean weight, mean weight of things. I like that. That's Jeff's creativity running dry. Oh well.
We took some things. We found this. What kind of things? Stranger Things?
All right. If you haven't seen the Stranger Things Charlie Brown Christmas mashup thing, you should look for that. It's kind of funny. Snoopy is the Demogorgon. If you have no idea what I'm talking about, I'm sorry. You're missing out on lots of good stuff. Any questions on how that kind of works? The places where you have a choice to make is, of course, right here. Do I use a T or a Z? And that really is totally if you know sigma or S. And the problem is not always going to use the letter S. You just got to say, where did this standard deviation come from that they told me? If it came from the sample, you got to use a T. If it's a population standard deviation, you're allowed to use a sigma. You're allowed to use Z. Okay. So that's section 8.2. Is all about T-score stuff. Confidence levels for T-scores. Now, what we're about to get into has so many layers to it. And that I know just sounds exciting. So I'm going to try to work my way up. And then I got this handout that explains all the steps. So when I learned this process, our teacher made us do 8 steps. I've cut it down to 5. So I need all 5 steps, right? Cut it down that far for you. Every step has a purpose, and I want to make sure you guys understand why we need all the steps. So here's the idea behind what we're about to do. If somebody makes a claim at all, some kind of, it doesn't even have to be mathematical, but let's keep it numerical for us. So they make a claim that they can bench lift this much on average, or that they can, let's see, what was I thinking about earlier? Let's do this. Oh, let me do that. Yeah. All right. Just kind of cut and dry, but it's going to help me out. So let's say there's a certain car. Let's say the Ford Focus. Oh, such a great little car. Has an average assembly time of 38 hours, right? Okay, so it takes on average 38 hours to put together a Ford Focus and get it off there, out in the world, doing its thing. They make a modification to the assembly time because they think that's just taking too long, right? The quicker we can get these things out, people are just wanting Ford Foci, right? Just, please. I don't think that's true. And now Ford leaves them. Now, once they make this tweak, they think the assembly time has decreased. So right there is a claim. They tweak the assembly process. And believe the assembly time is decreased. All right, before we get into any more specifics, I just want to ask you a question. If you watched one Ford Focus being created, and it took 36 hours, is that evidence that their claim is true? Why would it not be evidence that the claim is true? Yeah, I only saw one. I don't even know what the standard deviation is in the times. Maybe the standard deviation could be 20, right? So then 20. So if the standard deviation is 20, then 18 would not be a weird time to see. So if the mean really is 38, I really want this to make sense. If the mean really is 38 for any individual car that I watch, let me give you a standard deviation here. Yeah, say the standard deviation is 1 let's make it more interesting. 3.15 hours. So for one car, where would unusual go out to? Assuming this is, I'm doing a little bit more than I thought it would, but that's all right. Let's assume this is normally distributed. So for one car, how far out would I go to until it became unusual? Where's the maximum and minimum usual values? Yeah, you go 38. How far down would you go? 2 steps. I like it. So it'd be 38 minus 2 of these. 38 plus 2 of these. So what is this? 30.7? 31.7? So close, Jeff. That would be 44.3? Why do I keep wanting to go one more? Oh, I see why. Good job, John. 44.3. All right, so this is the hours. So if I went to one car, it could be anywhere from 31.7 to 44.3 and still be considered usual. Are you with me? So that's not even good enough. Even if I took one car and it was below this, that's still a 5% chance that happens. Something outside of here is a 5% chance of happening, right? So one car by itself is not enough evidence. So I've always got to take a sample of cars, or a sample of whatever. Right? So if I do a training program that's supposed to improve people's SATs, I can't say, my program works. Her score went up 200 points. No, that's not proof of anything, right? My drug works. This person's headache went away. Quickly. Take my drug. No. What? This guy could have been lucky, right? Do you guys kind of follow what I'm saying? So I need to take a sample. So let's say I take a sample. of, let's say 31 cars. Let's just do exactly the minimum we need to. It's an example of 31 cars. What was else? Oh, let's do something before we get even into this here. This is nice. Let's say, well, I'm trying to figure out how to get this next piece to make the most sense. This next piece is the one that's a little bit old, but also a little bit new. So we believe the assembly time has decreased, right? We think the assembly time has decreased. So when I find a sample, if I think that's true, if I work for them, and I think that's true, where do I hope my sample of cars ends up? Down here. So that's the idea of one tail. I'm only concerned about something down here. If it's anywhere up above here, I'm screwed. It's no good. So if I get a sample that shows up right there, then obviously my belief is wrong. I don't even do anything. I just go, it's wrong to begin with. Don't even have to do step one, right? Okay. So down here, and here's the whole idea. Even if I get a sample of cars that is less than, but it's not less than enough. So just the fact that I'm only taking a sample, I'm not looking at all the cars. I'm just taking a sample of cars. To be evidence that something is different, they don't just have to be less than the mean. They have to be less than enough. Just like these numbers kind of point to. They have to be far away from the mean. So let's say I want, let's see how this is going to work out. Let's say we take a sample of 31 cars and find average time of, what do you got, Jeff? 35.7 hours. Now, what do you think you're going to use statistically? What part of statistics? What thing have we been doing that tells me how far apart two data points are? How far away from the mean something is? Z-scores. They use standard deviations, right? I like it. So standard deviations are like centimeters or something, and z-scores are the ruler measurement. So I can see how far apart two things are. So, and that's the whole idea here. I want to see if what I see is so far below the mean that this can't be right. So, if this is right, if 38 really is the real average, and my tweak really didn't do anything, then my sample should be somewhere close to that. If that is the real mean, then the sample I pick should be something close to 38 hours. Do you guys understand that part? So if I find a sample that is so freaking far away from 38, what's more likely? That I just happened to pick a sample of really fast cars that were made, really took less time, or that that's not the right center? What's more likely is that's not the right center. The picture really looks more like this maybe. The mean is actually less. Okay. So the whole idea of a hypothesis, and believe me, we're going to go over and over this because it takes a little while for it all to sink in. But the whole idea is somebody thinks the middle is here, right? So I have to find a sample that is so far away from that it looks like they're wrong. So they're like, oh yeah, you think this? Well, look what I just did. That should have been almost impossible. It should have been almost impossible to get a sample way the hell down there. So that can't be the right middle. The middle should be lower down. Okay, maybe not. So right here, can you guys calculate the z-score for me? Let's see how far away this really is. How do I calculate the z-score? What's the formula for the z-score? And what do I have to do? Hopefully you guys... So here's the formula I really have to use. Because I got means, right? So I should know this. I can't use this number. What do I have to do? Convert it. So how do I convert it? So I can't use sigma anymore. I got to use sigma x bar. So what's that going to be? I take the old one and do what? Square root of 31. I like it. So anytime I take a sample and I'm talking about the sample means, I have to use the correct standard deviation. I can't use the one that was true for individual cars. I have to use the one that's true for groups of 31 cars. Real quick point. I did not just make a sample standard deviation. I didn't. This is still a population standard deviation. So if I had S, I'd still have to make S x bar. And still have to divide that by the square root of n. Maybe. So what do we get for this? We get, what's this first off? What's 3.15 divided by square root of 31? .566? Yep, cool. I like it. And now I can get the z-score. So it's our data point, 35 minus 0.7, minus the middle, which is still going to be, oh, what was it? Where'd it go? 38. Over the new standard deviation, the 0.566. It's like 4 points. Negative 4 point something. So make that 4 down. Negative 4.06. Now let me ask you this, after everything we've been through together, would you say that that z-score represents something that is very far away from the mean? Because that's outside of 2 steps, right? Which is the usual definition of usual, which is inside 2 standard deviations. That is way the hell down there. And in fact, if I wanted the probability that I get something in this area, I'd look at the probability that it's less than this, which the chart would tell me is 0.0001. Right? It's really almost 0% chance. So if this is in the right place, if that is the actual mean, we just did something that's almost impossible to do. Something with less than a 0.01% chance of happening. We just did it. So what's more likely? We just did something that unlikely? We just got hit by lightning? Or is the middle in the wrong place? I mean, the more likely thing is the actual time has decreased. So in real terms, the tweak they made did decrease the times. This is evidence. We've shown evidence that the average time is less than 38. Why? Because we got a sample that was so far below 38, there's no way that could be the right middle. So let me see this in a different way. So here's the idea. So I wanted to make sure that you understood there's going to be a lot of old calculations in this thing. There's a lot of steps. There's 5 steps. But every step kind of has old stuff in it. Right? So there's not a lot of new stuff here. It's just kind of repackaged a little bit. Let me try to hit you with a different idea. What if there was a teacher, somebody claims, oh, that teacher never gives anybody more than a, or that teacher very rarely gives more than a C to students. Right? And if you haven't hit one of these teachers, you will. Right? How would you show that they're wrong? If somebody said to you, oh, that teacher almost never gives out C's. If you found one person that got more than a C, is that evidence that they're wrong? Does that still fit into what they said? Yes, it does actually. If you found one person that got more than a C, that's not good enough to show that they're wrong. What do you have to do to find that they're wrong? You have to take a sample and find a lot of the people in your sample, or more than half, or something, right? A decent number of them got more than C's, randomly selected people. That would be evidence that they were wrong. So they thought the middle was like a C, and you find evidence, no, I found a higher average. I found so much higher than what you thought it was that you must be wrong. Maybe. So it's not good enough to find a sample. This sample was less than 38. Why didn't I just stop here? Because it could have been less than 38 just by random chance. But what's the probability that I took a sample that was less than 38 just by random chance? 0.0001. Holy shit. That is the chances that that just happens randomly. So is it more likely that it just happened randomly, or that the middle is just in the wrong place? It's more likely that the middle is just in the wrong place. All right. So let me ask you this. Looking back at this, I wanted to get through the nuts and bolts of this, but let's look back at this. What was the claim that was being made? What's the claim that's being made? Yeah, the assembly time, the average assembly time has decreased. So how do I write that in symbols? And we're talking about what kind of, we're talking about the average of the assembly time for everything. We think the entire assembly time average has decreased. So that is the population. So the claim that's being made is that the mean has decreased from 38 hours. So how do I write that? Less than 38. Now, anytime somebody makes a claim, even if nobody holds the counterclaim, there must be an opposite side to it. Right? At least one. So here in math, there is going to be exactly one. What is the opposite of this? Careful. The opposite of less than 38, it does involve greater or equal to. So for any claim that's made, you can mathematically determine the opposite of that claim. So the very first step in one of these problems is actually, they are called hypothesis tests. So the very first step makes sense. What the hell are your hypotheses? And you've all heard the word hypothesis. You all heard the pathetic attempt at a definition of educated guess, but oh well. All right, so hypothesis. So anything that has an equal sign in it, we're going to call that the null hypothesis. It's going to have a symbol H naught. H0. And yes, I do call it the hoe, right? Just because it's funny to say. Especially when we start talking about rejecting the hoe. That normally gets you guys more paying attention. So null hypothesis H naught. So in this case, the null hypothesis would be this. If it has an equal sign in it, if it includes the middle, that's what we call the null hypothesis. So in this case, the null hypothesis is mu greater than or equal to 38. Then there's another one called the alternate hypothesis. And in the other book I used, it was HA, which is nice, the hoes and the ha's. But now we get the hoes and the highs. And that's going to be the opposite, less than 38. So that would be step one. Step two would be, why are we allowed to do anything? And why were we allowed to do something here? I kind of said it as I did this, but why were we allowed to do anything here? What's the key thing to look for? We use z-scores and stuff. Why am I allowed to do that? Because... yeah, we knew sigma. But even before that, I have to know that it is normal. And it is normal. I didn't say it was normal, but it is greater than 30. Kick ass. All right, I like it. I like it. Okay, so let me do this. We've sort of gone over most of the big steps. We have one big step left to go, but I think it might be easier if I give you a little outline of what's going on. So every single hypothesis in the book, let me just say this right now. This is important. The book tells you to use a form that they have in the back of the book. Screw that form. You're going to do this for the hypothesis test. These steps. You guys kind of with me. They're going to change a little bit. There's still going to be 5 steps. They're still going to mean the same things, but when we do a test for a percentage, some of the formulas are going to change. Yes?
So in step 1 is all of that. Step 2 is describing why it's...
oh yeah, it's all on here. Let me give it to you. Got all the steps on here. You guys look as excited as you should.
Oh.
So there's one step in here that is quite different from what we're used to, and that is step C. So we're going to talk about that when we hit it. Oh, yeah. Let's start this off here. I like this problem because this kind of explains why sometimes I can know the population standard deviation. So there's a known average lifespan for these, what are they, Minnesota coyotes? Yeah, Minnesota coyotes, how long they live. There's a known mean and a known standard deviation. So I'm looking at a subgroup of those coyotes. So they still have the same population standard deviation. They're still a part of that population, which is why sometimes I can know sigma. So I just gave away that we know sigma here, so what am I going to be able to use? I like it. Wow. That is really zoomed. Alright. So what is the claim that's being made? If you had a chance to read this through, what's the claim that's being made? Yeah, in English it's the Minnesota coyote lives longer in captivity than they do in the wild. Now I need to convert that into math. So the mean lifespan, I think, is greater than what?
7.25.
Beautiful. 7.25. That's the population mean right there. That's for all Minnesota coyotes. I'm going to compare that to the subgroup of Minnesota coyotes that were captured and put into captivity. So which one is that going to be? The ho or the high?
High.
Yeah, why is it going to be the high? There's no equal sign. I love it. So the claim could be either one. If my claim was, I claim the average is 7, mu equals 7, that would be HO. That would be the ho. So if it has an equal sign in it, it's the HO. If it doesn't, it's the H1. So this does not have an equal sign. It's the high. So what's the ho going to be?
7.
Less or equal to? I like it. Cool. How many tail tests will this be? If I am the one doing it, if I'm Phil, and I believe this, where do I want my sample of coyotes' ages to show up? Yeah, I'm going to want it to show up here. So how many tail tests is this? 1. It's crazy. So when will it be a 2-tail test? If my claim was, I think their average is 10, what's the opposite of that? Not 10. So how could it be not 10? You could be bigger or less. That would be when it's 2 tails. Or if my claim was, I think it's not 10, then obviously that would be 2 tails. I like it. But when you see a word like we think it's decreased, we think it's less, we think it's gone up, we think it's more now, that's going to be 1 tail in that direction. So this is a 1 tail. And again, this is why that T-score chart is set up with 1 tail, 2 tail, to go along with what kind of hypothesis test we're doing. I like it. Wasn't that nice of them to do that? It was crazy. So step 1 is, what the hell are we talking about? Makes sense. That's where you start. What the hell are you talking about? This, okay. Step 2 is, what can you use to talk about it? Can I use Z-scores, T-scores, or nothing? And why?
Oh no.
So first off, why do I know it's normal? Yeah, n is 36, which is greater than 30. Check. Secondly, do I know sigma or S? Population standard. So it almost has to be that in your face when it's the population. They're going to have to say, it is known that for all coyotes or something. They got to make it like they're referencing the entire population. Normally, if you can't find anything, that's a sample. We took a sample, we found a standard deviation of 7. That came from the sample of shit. But they're going to make a big deal of it if it's the population standard deviation. So this sigma is known, so what can I use? Say it again? Z. Z is in zebra. I like it. Z-scores. So there's a purpose for every step. Bless you. Step 1 is, what the hell are we talking about? And it also kind of helps me set up where my evidence is going to be. Step 2, what can I use to investigate this? Now, this is the weird step. This, I kind of told you this was going to happen. So, in the early part of this semester, we talk about unusual starts at 2 steps out. That is remarkably arbitrary, but that is the most often used one. But it could depend. If I'm talking about a nuclear reactor, and it spits out a little error of, if it starts to get a little bit away from where it's supposed to be, I'm up and out of my damn seat and going to see what the hell's going on. So my tolerance for it being off is very low. So I would use a very low, I would say if it gets to here, I'm going to go take a look. I'm not going to wait for it to be over there. You guys with me? So if there's something in a nuclear reactor, it should be here. And it gets here. I'm out. I'm going. What the hell's going on? So I want a big-ass tail, right? Very strange day, I know. I would want a big old tail. Why? Because I want anything in a big tail so that gets me closer to the mean. So I just want to get a little bit away from the mean, and then I'm up and down on my chair. I'm going to see what's going on. Something blocked. Water's not flowing. Godzilla's coming. I don't know. Something's happening, right?